Hello and welcome to this video about determinant proofs. In this video we'll prove this equation, that this determinant sum is true given these conditions. All of these matrices must contain the same entries everywhere except in row M. In row M the entries in matrices B and C are allowed to be different, and the entries in row M of A must be equal to the sum of the corresponding entries of B and C. So here's an example of what I'm talking about. You can see that outside of row M all of the entries are equal, but in row M inside the green boundaries the entries in A are equal to the sums of the entries in B and C. So here's a more concrete example of these matrices using numbers. 3 of the rows of all these matrices are identical, but the third rows aren't. I've circled the entries in this row. So now when we construct matrix A, 3 of the rows are identical again, but the third row isn't. It's made up of the sums of the other entries in the other 2 matrices. And so this is what matrix A is after we've calculated it. These matrices should obey the theorem. Now to start this proof, we'll define these matrices by defining their entries in this case notation. The entry of A can be whatever we want it to be, except for in the mth row, where we'll set it to be equal to the sum of the entries of the other matrices in this row. And the entries of matrix B can be anything if they're in the mth row, but they must otherwise be equal to the entries of A. I'll just scroll everything up the screen here to make more room. And C is similar to B. It can have any entry in the mth row, but the entries must equal A's entries in all the other rows. So I can grab some equations from these equations to use more directly in this proof. The entries in A are equal to the sum of the entries in B and C in the mth row. And all of the entries of these matrices are equal to each other in all of the other rows, like this. We have to write the additional condition that I isn't equal to M. So now to start the main part of this proof. We'll start with the determinant of A and expand it out according to its definition. Sigma is equal to any one of the permutations of length n, and all of these products in the sum are added together for all of the permutations of length n, which is the size of matrices A, B and C. So I'll just scroll everything up the screen here to make some more room. We can expand this product out to include the entries in and next to row M. Then we can make this substitution, since the entries of A in the mth row are equal to the sums of the entries of matrices B and C in this row. We can then split this sum, because this is a property of terms added together in brackets. I'll just scroll everything up the screen again to make some more room. We can then make this substitution for the entries of A because of this equality, when they aren't in the mth row. Then we can make this simplification because there's no need to especially focus on the mth row anymore. So I'll just scroll the screen up again here. And these terms are equal to the determinants of B and C by definition, so now we've proven this theorem fairly easily. And I'll just put the result that we've proven in a box like this. So that's it, we've proven this theorem. I found another version of this proof online, but it was much more complicated. They left a lot out, and I couldn't get it to work. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.